Solving system of differential equations by exponential and SAS method and matrix method. So we have these two differential equations. Dx by dt is equals to x plus y and dy by dt is equals to x plus 5y, and we need to solve them, right? This matrix method is super cool, and I believe that everyone should be like, if you're watching this video, definitely check the matrix method. Even though you might want to skip, that's fine. And first of all, I will definitely do it by exponential and SAS method. This is just German word, and its meaning is assumption. What we will do is we will assume that the solution is an exponential function, and then we will go on. And yeah, I'll also give you the reason why we will assume that. Okay. Now, first of all, like to use the first method, we need to combine these two equations into a single one, and then we will use that. So over here, you might notice that y is just dx by dt minus 5x, right? So if we use this from the first differential equation and substitute in second one, substituting y is equals to dx by dt minus 5x in the second one. Now what we get is d by dt of dx by dt minus 5x will be equals to x plus 5 times dx by dt minus 5x. Now this is entirely just based on x, and there's no y, and now we just need to solve these ones, and that's a benefit. Now this will just be d square x by dt square minus 5 dx by dt is equals to x plus 5 dx by dt minus 25x, and that becomes d square x by dt square minus 10 dx by dt plus 24x is equals to 0. Now over here, over here, notice that this is no differentiation in the first differential, second differential. For these things to cancel and exactly become 0, you might feel that dx by dt should be something like the exponential, right? Let's say to the power rt, so that even though it's differentiated, it will just be r times e to the power rt, and again if it's derivative, r square e to the power rt. E to the power rt is conserved, and all the remaining this r square, these coefficients, we can definitely choose r in a way that just cancels among each other and becomes 0, right? So that's our idea. So that's why we are going to assume that the solution is just 1. Oh, I mean to say just x is e to the power rt, so that dx by dt, I'm sorry, I wrote differently than what I was telling. Okay, yeah. So yeah, let's do that. Now over here, we will assume x is equals to c e to the power rt is the solution, right? Because yeah, definitely I can definitely also generalize this solution with the c, because even though they're c, the same solution is going to hold true, because c can just be taken common, and that's still c times 0 is still 0, right? Okay, so now if this is the solution, now we will just have c r square e to the power rt over here minus 10 cr e to the power rt plus 24 c e to the power rt is equals to 0, right? If you substitute, now we are assuming this is the solution, and now we are trying to find the value of r and c, right? Okay, now over here you can take c e to the power rt common, so this will be r square minus 10r plus 24 is equals to 0, right? So this is a positive, that cannot be constant. Definitely, even when this c is 0, x is equals to 0 is definitely a solution, but we are not interested in that trivial solution, right? We are not interested in that, so we definitely don't want to make c 0. So if these two are not 0, then the only solution is when this is 0, right? So r square minus 10r plus 24 is equals to 0. And this will be r square minus 6r minus 4r plus 24 is equals to 0. R times r minus 6 minus 4, r minus 6 is equals to 0. R minus 6, r minus 4 is equals to 0. And r is equals to 6 or 4. So that means there are two choices for r, right? So basically I can say that like both of the c to the power 60 and c to the power 40 will be the solution. And as a result of that, their sum will also be a solution, right? Yeah, c1 and c2. So yeah, those constant can be different according to the initial conditions, right? So yeah. Okay, so this is general solution, and this also includes both solution, right? Because if you just want the second one, c1 can be 0. If you just want the first one, c2 can be 0. And also, even if both of them are there, still still this should also satisfy this differential equation. You can check, because the plus sign doesn't really hamper, because differential is also linear. Okay, so we got that this is the solution, and now we need to find c1 and c2, right? Okay, I just forgot to mention that in the question it has also given x of 0 is 1000 and y of 0 is 3000. This is also given, and if we use this, now I will also need the equation of y of t before I try to find c1 c2 using this initial values, right? And over here these are basically the values of t, okay, because x is a function of t over here. Now we know that y is equals to dx by dt minus 5. So I can use this equation to find y of t. Y is just dx by dt minus 5x. We know that x is this thing over here, this solution. So y will just be c1 6 e to the power 60, right? That comes in front, plus c2 4 e to the power 40. That's the derivative, minus 5 times c1 e to the power 60 plus c2 e to the power 40, right? So our y of t will be 6c1 minus 5c1 is c1 e to the power 60. 4c2 minus 5c2 is minus c2 e to the power 40. So our y of t becomes c1 e to the power 60 minus c2 e to the power 40, right? Okay, now you can just substitute the initial values and find c1 c2. We know that x1 x of 0 is just c1 e to the power 0 plus c2 e to the power 0, and this is also 1000, right? Yeah, and y of 0 is c1 e to the power 0 minus c2 e to the power 0 is 3000. Now you can use this to find c1 c2. 2c1 is just 4000, so c1 is just 2000, right? And if we subtract these two equations, we will have 2c2 is equals to negative 2000, so c2 is equals to negative 1000. So we got the c1 c2, and therefore the solution would be x of t is 2000 e to the power 60 minus 1000 e to the power 40, right? And y of t will be 2000 e to the power 60 minus 1, sorry, this is plus 1000 minus 1000 e to the power 40, and these two are the solutions of the system of differential equation. Now this is from the first method, and now the second method, the more interesting one. Now second method is the more interesting one, so let's dive into that. So I guess you guys know like how we solve like simple linear equations using matrix, right? Similar to that, now we are going to use that same idea over here. We'll first try to write it as matrix multiplication. So we'll try to write it as dx by dt dy by dt is just now I can write it as 5 1 1 5 xy, right? You can write it in this form, right? We have always been doing this. Now, uh, now, okay, let me say that this is my A matrix A, and this is my x vector. I can represent x vector but also by in this way by giving a tilde symbol, and I will represent this by x dash with a tilde, right? Now, if I denote it this way, I just have x tilde. I just want to make it look like it's normal, simple variables, right? Even though these are actually vectors, right? We can like to solve this differential equation. Now we can just look them as normal variables, just x, y, and such. With like, we can just see them as normal variables and not the uh, vectors, right? So now this will just be d of x tilde over dt, right? And over here this will just be basically this is almost like taking a derivative of vector xy, I mean where xy variables, and this being dx by dt and then dy by dt, which is almost similar, so you can just see it as parables. Yeah, and this is just x times x tilde. Now again, x tilde is just a vector actually. Now I can write it as d of x tilde by x tilde is equals to a dt, right? Okay, now if we integrate both sides, now see that this integration it's just not obeyed by some variables, this is also obeyed by vectors with the variables in them. Integrating both sides that will be log, and also we can define log for vectors using the series. Yeah, we'll definitely look into that. Now the log of this x tilde will just be ta plus some constant c, right? Okay, and this c we will need to have a same order as the other vectors, and then our x tilde will just be e to the power ta dot e to the power c, right? Now at t is equals to 0, x tilde will just be x tilde at 0, right? X tilde at 0, right? So using this, our x tilde at 0 will just be e to the power 0 times e to the power c. So e to the power c is just x tilde at 0. So therefore, our x tilde is just e to the power ta times x tilde at 0. Notice that I'm trying to write the constant at the backward, because for the multiplication to happen, basically this e to the power ta, where if A is a 2 by 2 matrix, this entire thing will also be 2 by 2 matrix, and for the multiplication of 2 by 2 matrix and 1 and 2 by 1 vector, to for the multiplication to happen, the order needs to be this one. If I swap, then 2 by 1 2 by 2, this multiplication cannot happen, right? So yeah, this order is important right now. Okay, so we got this, right? Now we will try to use this. So we basically have solved this uh, basically this differential equation using considering just vector or like a system of vectors with variables as single variable. And yeah, that's actually a powerful idea, because it helped us, like it simplified things a lot. Now the only problem is how to take exponential of matrix, but yeah, we will do that, that will not be a problem. Okay, now I guess you know that this x tilde is just xy, and this x tilde of 0, this is just initial condition, x0 y0, and we know that that's just 1000 3000, right? Okay, don't forget that. Now the only problem is how to find e to the power tm. Though the normal exponential is not defined, we can define this using the series, right? Sum from n equals to 0 to infinity of ta to the power n by n factorial. And we can definitely find the nth power of matrix, right? For zeroth power, you can consider the matrix to become I, First power, from the first power, all are defined. It's just like multiplying the matrix twice, thrice, four times, five times, and so, right? Now let us see, like, even though, okay, first of all, this will become t to the power n, a to the power n by n factorial. Even though we know that a to the power n is actually just multiplying it n times, but how will we even find the result of a matrix being multiplied 100 times or 200 times? That would be too tedious, right? But like, no, don't worry, we do have some ideas. I guess you guys, I think I explained this in one of my previous videos where I find cosine of a matrix, like how we do that. And in this video, like I will directly go to finding eigenvalues and eigenvectors, and I won't really explain a lot about them. If you want, like, I will comment the video where that's explained, but for now we'll just go directly. So we know that our matrix A is 5 1 1 5. So now what we will do is we'll use the theorem that this matrix A can be written as PDP inverse, where P is the matrix with eigenvectors A1 B1 and A2 B2. These are two pairs of eigenvectors, and D is just the matrix with eigenvalues lambda 1 and lambda 2, and P inverse is just A1 B1 A2 B2. We will use this theorem that a matrix will just be equals to PDP inverse, where P is matrix of eigenvalues and D is matrix of eigenvectors. And the benefit of writing it in this form is that once we have all these three matrices, then we can just find a square uh, by multiplying this two times, right? But since there's P inverse and P like alongside each other, we can just group them using associativity. Wait, I will charge it. Yeah, and just group that just becomes I, right? So this will eventually become P d square P inverse. And yeah, so again, if I even take P a cube, you can do you can go similarly, and this will be P d cube P inverse. And the benefit is it's really easy to find the nth power of diagonal matrix, because for diagonal matrix, like over here for our case, nth power will just be lambda 1 to the power n lambda 2 to the power, and you can check that by by just simple multiplication you will be able to verify this result. You can check it for yourself. So that's the benefit of, I'm sorry guys, so that's the benefit of writing it in this form. So let's try to find eigenvalues and eigenvectors so that we can find the nth power of A by just finding the nth power of D, which is actually easy. Okay, so now to find eigenvectors, we just we go to the we go through its definition that eigenvectors and eigenvalues are defined as eight for a matrix A. Eigenvector is such vector such that if it's multiplied to it, the vector just gets scaled. So this is the definition. We will use this one. If I bring it to other side, we will have a vector minus lambda b vector is equals to 0. Taking b vector common, I will have a minus lambda. And since this is a 2 by 2 matrix, I will also introduce I over here. Just this is just the like matrix for version of number 1, so as to make the things doable, right? Because we can definitely do matrix minus number is equals to 0. Now notice that like our neither of these things will be 0, right? Because definitely this eigenvector should not be 0, and also another will not be 0 since a is not 0. And even though both vectors aren't 0, it's possible that they become 0, right? For that, in transformation, they need to scale down. Okay, so for now, like we do know that in the like transformation where it's being scaled down, determinant should be 0 for this a minus lambda I, which is our transformation matrix. But you can also see it this way. So basically, if let's say if the determinant of a minus lambda is not 0, then you can take inverse. then our b vector will just be a minus lambda I inverse times 0, which is 0, right? So this is a 0 matrix, okay? Like, I mean 0 in the vector form, not just a 0. So anyways, that's going to be 0. But this gives a contradiction that b vector is 0, which is not possible. So yeah, a minus lambda I cannot have 0 determinant. I mean, a minus lambda I should have 0 determinant so that it cannot have inverse. So this implies that a minus lambda I should have determinant 0, and this can be used to find lambda. And that becomes determinant of 5 minus lambda 1 1 5 minus lambda is equals to 0. So this becomes 5 minus lambda square minus 1 is equals to 0. This is lambda square minus 10 lambda plus 24 is equals to 0. Notice that this equation is actually same as this equation over here, and that's not just a coincidence. There's reason behind that which I want you to explore. So this becomes, now we know that this is lambda minus 6 lambda minus 4 is equals to 0. So lambda is equals to 6 or lambda is equals to 4. These are our two eigenvalues, and corresponding to them we will also have eigenvectors. Again, to find them we will use the definition itself. We know that a b vector should be lambda b vector. Our a is 5 1 1 5. B vector we don't know, let's say a1 b1 should be equals to 6 times a1 b1, right? That means we should have 5a1 plus b1. a1 plus 5b1 is equals to 6a1 b1, right? So that means 5a1 plus b1 is equals to 6a1, which further implies that b1 is equals to a1. Again, a1 plus 5b1 is equals to b1, which implies that, sorry, 6b1, which implies that a1 is equals to b1. Now notice that for this we just need both a1 b1 vector to be just the same thing, t, right? They just need to be same. I can take t common and make it 1 1, right? So basically there will be a line of vectors that satisfy it, but we just need one of them, and we will take the most simplest one, 1 1. So I can say a1 b1 as 1 1. Anything will work, but this is like a nice one. Now again, for next solution we will go to the same process. We will again use the definition that a b vector is equals to lambda b vector. A is 5 1 1 5 and a1 b1. Now a2 b2 is equals to, now this is again 4 times a2 b2, right? So this next one is 4, right? Yeah. So 5a2 plus b2 will be 4a2. a2 plus 5b2 is equals to 4b2. So this is a2 plus b2 is equals to 0. And this is also a2 plus b2 is equals to 0. The solution will typically be a2 b2 will be a t and minus t, right? So that they will be 0. Now if I take t common, this will just be 1 minus 1, right? Okay, so these two are the solutions with the eigenvectors. I can just take a2 b2 as now 1 minus 1, right? Okay, so now I know this. Now I can write our matrix as, okay, now I can write our matrix as our p is just our first a1 b1 is 1 1, second is 1 minus 1, and lambda 1 is, first one is 0, second one is 4, and then its inverse. So 1 1 1 minus 1 inverse, right? Okay, so now we have a, we can now find the sum. So this sum, we basically want to find e to the power 2a, right? Because if we have this, I can just substitute it over here, right? Yeah. So now let's try to find this. So this will just be sum from n equals to 0 to infinity t to the power n by n factorial. A to the power n is just nth power of, okay, again, I already told you that if you want to find e to the power n, just this diagonal will have n, right? Just this nth will be carried on to diagonal, right? So I will just write it in that way. So others will be as it is. I will just have 1 1 1 minus 1 as it is, and this will have the nth power. But again, I also told you that the nth power of the d will carry it on to the elements. So 6 to the power n, 4 to the power n times 1 1 1 minus 1 inverse, right? Now notice that like these two are, this one is actually just a constant in average in the entire sum, right? So I can take it out of the constant. This is also constant, so I can take it out of the sum, right? So I can actually write it as 1 1 1 minus 1 times the sum from n equals to 0 to infinity t to the power n by n factorial 6 to the power n 0 0 4 to the power n and then 1 1 1 minus 1 inverse, right? Okay, now after this what I can do is, now I can just take this constant inside the sum, so this will be 1 1 1 minus 1 and sum from n equals to 0 to infinity. This will just be t to the power n 6 to the power n by n factorial 0 0 40 to the power n by n factorial, right? And I will just have 1 1 1 minus 1 inverse. Now we know that again when if it's being summed, like all the corresponding elements of matrix will be added. So this will just like this will be same as, this will almost be same as just adding the all the components over here, right? Adding all the components over here. This is just 0, so this will just be 0. This will also just be 0 and adding all the components over here, right? So yeah, it will just be like this and 1 1 1 minus 1 inverse. And this is now 1 1 1 minus 1. And now we know that this is again the definition of e. So e to the power 60 0 0 e to the power 40, right? And this is just 1 1 1 minus 1 inverse. Okay, so now if I try to multiply these things, do I want to multiply? I guess wait. So okay, so let me, I will multiply it later on. So okay, now if I have this expression 1 1 1 minus 1 and e to the power 60 0 0 e to the power 40 1 1 1 inverse, let me substitute it back over here. Now we know that my solution x tilde is just the e to the power this thing, and which I just found out 1 1 1 minus 1 e to the power 60 0 0 e to the power 40 and then 1 1 1 minus 1 inverse. And now my x tilde at 0 is just 100 200, right? Yeah, so this is my solution. And x tilde, I guess you guys know that this is just x of t y of t, right? Okay, now let me first go find the inverse over there. So this will just be okay, so this will just be negative 1 by minus 2, right? 1 by minus 2, and then this will interchange minus 1 1, and that will just be minus 1 minus 1, right? Okay, 100 200. Yeah, this is interchange. All this will just carry a minus sign. Now again I will just write it as half so that I can use the negative sign to multiply that matrix e to the power 60 0 0 e to the power 40. So this will just become 1 1 1 minus 1 100 200, right? Okay, now this will be half of 1 1 1 minus 1. Let me multiply the last two matrices. Let me multiply the last two matrices. This should be 100 plus 200 100 minus 200, right? Okay, this is satisfying because the answer is reducing a lot into simpler expressions. This is half 1 1 1 minus 1, and now that's just 300. It's just minus, okay, let me write it first. 60 0 0 e to the power 40, that's just 300. It's just minus 100, right? Again let me multiply the last two. X tilde is just half 1 1 1 minus 1. This is just 300 e to the power 60 minus 100 e to the power 40, right? Again let me multiply these two matrices again. Half of 300 e to the power 60 minus 100 e to the power 40, 300, yeah, e to the power 60 plus 100 e to the power 40. Wow, yes. Okay, what is the answer, guys? Is it matching or not? No, I cannot expect it to not match, guys. I cannot. Oh, so there's 2000, 1000, right? Guys. I don't want that. So this is basically, first of all, this is just 1000, 2000, but that doesn't really matter, right? Because the zeros just carry on. Guys, I didn't want this. And hey, is it really not matching? Why? 7 plus 3 to 1000, 3000, 2000 and minus 1000. Mm, okay. So, mm, 3000 minus 1000, 3000 minus 1 plus 1000. Now, if I take half, wait, like, is there a problem? How can there be a problem? Wait, the problem is this is not 2000. Second one is not 2000. Second one is 3000. Man, this is 3000. In the initial condition is 1000 and 3000. I just hate it. I just hate it. Thank God there was not really a mistake. Because I cannot imagine making this video again. Like, that would be so troublesome. Okay, so now this is 3000, 3000, 3000, and 3000, 3000. So 4000 and minus 2000. And this is just 4000 minus 2000. So this is again 4000 e to the power 60 minus 2000 e to the power 40. The first equation has minus sign, right? No, again there's a problem, guys. The first is plus. How come? How come? But how come the first has plus? Mm. Guys, no. I have done wrong over here. First one should have minus because C2 is minus 1000. So if C2 is minus 1000, this should be minus. I have made so many mistakes here. Because C2 is minus 1000, this should be minus. And minus or times minus 1000, this should be plus. Guys, I'm sorry for this. Okay. And this is 4000 e to the power 60 plus 2000 e to the power 40. So x tilde, which is basically just x of t, y of t is just now take the half. So 2000 e to the power 60 minus 1000 e to the power 40, 2000. So 2000 e to the power 60 plus 1000 e to the power 40. So the first one is just x of t, second one is just y of t. And now the solution, these two solutions exactly match, and that's the moment of happiness, right? But anyways, I made a lot of mistakes, so I'm sorry for that. But I do hope you got some new insights that we can even treat vectors as normal as numbers, and then differentiate them, exponentiate them, raise them to like Also integrate, we can also integrate vectors, also we can raise them to exponential. We can do a lot of things with vectors as much as we can do with numbers, and that's really powerful thing. We saw that it's really powerful, right? It could solve a system of differential equations. Now let's say for two such equations we can definitely do it this way, right? But what if there were a lot, there were around three, four systems? We definitely need matrix, right? And even though how many systems are there, this X vector would still be just a simple thing. And yeah, this is really powerful. Just like Cramer's rule is powerful for higher dimension, this is also powerful for higher dimension. And I guess you guys get the idea of how to do it. And I think this will be helpful. If yes, do share with your friends. Thanks for watching and look forward to seeing you in the upcoming videos too.